The phone in your pocket today is more powerful than the NASA that sent us to the moon. The world's fastest supercomputers can simulate galaxies. We are the gods of computation. But this is an illusion. The number of possible sequences from a coin toss just 266 times exceeds the number of all atoms in the universe. This is a wall of complexity that even our most powerful computers couldn't solve in billions of years. This is why we needed something different. And we understood what that something was when Google's quantum processor finished a task in 200 seconds that would have taken a supercomputer 10,000 years. But what's truly shocking is how this power works. It doesn't copy reality, it bends it. If you are also curious about the secret behind this impossible power, subscribe to the channel and turn on notifications, because now you will see how reality is broken. We begin. For years, we thought computers were only about speed. Each new generation was faster. It had more processing power. It's a fact that your smartphone right now has more processing power than all of NASA had when they sent humans to the moon. But this doesn't mean we can solve every problem, because some problems are so fundamentally complex that even if all the computers on Earth worked simultaneously for billions of years, they could not be solved. This isn't because the computers are slow. It's because the problems themselves exist in a dimension of complexity that machines operating on a binary system can structurally never reach. And this is exactly what quantum computers change. Therefore, to understand this new world, we must start from an unexpected place: a coin. Imagine you toss a coin 20 times and record each outcome. The probability of any other person on Earth getting the exact same sequence of heads and tails is roughly 1 in a million. This sounds manageable. But now, imagine you toss the coin 100 times. The number of possible sequences exceeds the number of atoms in a visible star. This is an incredible leap, because we are not talking about a linear increase here. And now, we come to the truly shocking part. When you toss the die 266 times, the total number of possible sequences surpasses even the most common estimates for the number of atoms in the entire observable universe: 2 to the power of 266. This number is so large that if every person on Earth used a computer that could count 10 billion sequences per second, it would take longer than the age of the universe to list them all. Extend this to 10 billion Earth-like planets, with 10 billion people on each and the same computers on each, and it still wouldn't be enough. Add 10 billion galaxies, 10 billion universes on top of that, and you would still fail. This is not a mathematical curiosity. This is a fundamental statement about the nature of complexity. There is a reason this matters. Because the universe is not simple. We just evolved to think in patterns because it helped us survive, not because it reflects the true structure of reality. This tension between human cognition and cosmic complexity is at the very heart of why quantum computing exists, and why it represents something truly different in the history of human technology. But to understand what this new technology is, we must first grasp what our current technology does, and where it falls completely short. We must know why classical computers hit this wall, because every classical computer, from a pocket calculator to the world's fastest supercomputer, runs on bits. A bit is a switch. It is either off, representing a 0, or on, representing a 1. Everything your computer does, every email, every video, every financial transaction, every weather forecast, is a result of billions of these switches flipping on and off in precise, predetermined sequences. The operations are deterministic. They proceed step by step. They are sequential, one state at a time. When you take a digital photograph, the image is stored as millions of pixels, and each is encoded in binary. Classical computers perform these tasks perfectly, because they reduce everything to a manageable linear sequence. But some problems refuse to remain linear. So, for example, consider a simple molecule like caffeine. Caffeine contains dozens of atoms, and these atoms interact quantum mechanically. This means their electrons exist in complex, overlapping states that cannot be captured by a binary system. To accurately simulate the behavior of caffeine on a classical computer, you would need to track every possible quantum interaction between every electron in every atom simultaneously. This is computationally punishing even for caffeine. For larger molecules like proteins, it becomes effectively impossible. Therefore, we are not facing an engineering limitation that better processors will solve. This is a mathematical wall. The number of states you need to track grows exponentially, meaning it doubles with each added atom. And exponential growth defeats even the fastest classical hardware. Classical computers were built for a specific class of problems, and quantum mechanical simulation is completely outside that class. The same issue arises in cryptography, optimization, drug discovery, materials science, and dozens of other fields. The problems are not hard because our computers are too slow. The problems are hard because their very structure demands a type of computation that binary architecture cannot provide. To break through this wall, we need a different language, a different logic. But what could this language be? The answer lies in the language that nature speaks at its most fundamental level: quantum mechanics. The basic unit of quantum computation is the qubit. Unlike a classical bit, which must be either a 0 or a 1, a qubit can exist in a superposition of both states at the same time. This is not a metaphor, it is not an analogy, it is a direct consequence of quantum mechanics. The same physics that explains how electrons behave around atomic nuclei and how photons travel through space. To understand superposition intuitively, think of a spinning coin in the air. Before it lands, it's not secretly either heads or tails and you just don't know which one. According to quantum mechanics, it genuinely exists in a combination of both possibilities. The state only collapses to a definite outcome, either heads or tails, when a measurement is made. Qubits behave in the same way. A single qubit holds both 0 and 1 at the same time until it is measured. Because of this, computational power increases at a mind-boggling rate. A system of 2 qubits holds 4 states simultaneously. 10 qubits hold 1024 states simultaneously. The scaling is exponential. N qubits hold 2 to the power of n states at the same time. This makes a huge difference, because with 300 qubits, a quantum computer can represent more simultaneous states than there are particles in the observable universe. This is not a performance metric. It is a fundamental statement about the nature of information. Classical computers process one state at a time and only simulate parallel processing. But quantum computers genuinely exist in all these states at once and process them in parallel on a physical level. But superposition alone doesn't make a quantum computer useful. The second principle, entanglement, is where things get truly extraordinary. When 2 qubits become entangled, they enter a shared quantum state. This means that measuring one qubit instantly determines the state of the other, no matter the distance between them. Einstein called this spooky action at a distance, and he spent years trying to prove it wasn't real. But he was wrong. Entanglement allows the qubits in a quantum computer to be coordinated. They are not just individually in superposition, they are collectively entangled. They form a computational fabric of interconnected probabilities. SO, how do you find the right answer among all these possibilities? The point is not just to create infinite possibilities. The point is to control those possibilities and steer them toward the right result. And this brings us to the third and perhaps most important principle, the mechanism that separates the answers from the noise. Because without this mechanism, all we would have is a meaningless quantum mess. The name of this principle is quantum interference. And this third principle, quantum interference, is the mechanism that allows quantum algorithms to produce genuinely useful results, instead of just generating noise. What does this mean? Think of it this way. Like waves on the surface of water, the probability amplitudes of different possibilities, which are the mathematical quantities that define the probability of different outcomes occurring, can either reinforce or cancel each other out. Quantum algorithms are designed so that the probability amplitudes corresponding to wrong answers cancel each other out, while the amplitudes corresponding to the right answers reinforce each other. Therefore, when a measurement is made, the system collapses to a state that is, with overwhelming probability, the correct answer. This is why quantum computation is not just about brute force. Rather, it is about orchestrating interference patterns across exponentially large state spaces so that useful information emerges naturally from the quantum computation. It's like conducting an orchestra. Each instrument qubit plays its own note, superposition, but the conductor, the algorithm, arranges them in such a way that what emerges is not a cacophony, but a perfect harmony, the correct answer. But this elegant harmony also has the potential to shatter one of the most fundamental security structures of our current world, because the encryption that protects your credit card number when you shop online relies on a mathematical problem called integer factorization. The idea is simple. It's easy to multiply two large prime numbers together to get an even larger number. But reversing this process, starting with the large number and finding the two prime numbers that produced it, is a computational disaster for classical machines. Current encryption standards use 2048-bit keys, and factoring a 2048-bit number with classical hardware would take longer than the current age of the universe. This is our digital fortress. But in 1994, a mathematician named Peter Shor developed an algorithm that runs on a quantum computer and factors large numbers in polynomial time. This means the computational cost increases manageably as the numbers get bigger, not exponentially. A quantum computer running Shor's algorithm could break 2048-bit RSA encryption in a matter of hours. This is no longer a question of if, but when. Therefore, quantum mechanics is not just a sword, it is also a shield. Quantum key distribution, known as QKD, offers a secure communication alternative that doesn't rely on computational difficulty at all. Instead, it uses the laws of physics directly. The protocol, developed in 1984 by Charles Bennett and Gilles Brassard, works like this. A sender transmits information encoded in the quantum states of single photons. Because measuring a quantum state disturbs it, any eavesdropper trying to intercept the photons will necessarily leave a detectable trace. The two parties can then compare a small sample of their results to verify if their communication has been compromised. If the comparison shows no discrepancies, they know the key is secure and can use it to encrypt their messages. If discrepancies arise, they know someone was listening, and they discard the key entirely. The security of quantum key distribution does not rely on mathematical assumptions. It is based directly on the structure of quantum mechanics. No future advance in computational power can undermine it, because the protection comes not from the difficulty of solving a math problem, but from the physical impossibility of measuring a quantum state without disturbing it. And this is not theoretical, it is operational. Financial institutions, government agencies, and defense organizations in many countries are already using it to protect their most sensitive communications. But what quantum computers can do is much more than just breaking and making codes. Optimization is another area where quantum computing offers capabilities that classical systems cannot match. Consider the challenge of routing a delivery fleet in a city with hundreds of destinations. The number of possible routes grows factorially with the number of stops. This means it grows faster than any polynomial and almost any exponential function. Classical computers handle this with heuristics, which are clever shortcuts that find good solutions without guaranteeing the best one. But quantum algorithms can explore the entire solution space in ways that classical heuristics cannot. They can find true optimal solutions instead of approximate ones. The same logic applies to airline scheduling, traffic management, logistics networks, and portfolio optimization in finance. Each involves vast combinatorial spaces where the classical approach leaves measurable inefficiency. Quantum optimization doesn't just save time, it unlocks genuinely better outcomes that classical machines are structurally prevented from finding. This means less fuel, less traffic congestion, and a more efficient world. Superposition, entanglement, and interference. These three fundamental principles explain why quantum computers are different. They are not just faster calculators. They are a completely new kind of information processing, using the fundamental operating system of the universe to unlock the doors to problems that classical computers would remain locked out of forever. We have understood the concepts, we have seen the potential, but what do all these theories turn into in the lab, in the real world? What have these machines, using these principles, actually achieved? Because There is often a huge gap between the beauty of an idea and the reality of engineering, and when scientists tried to cross this gap, the first concrete results they encountered proved something that left everyone breathless. And that proof. And now comes the real shock, because these theoretical principles did not remain in the silence of laboratories. They leaked out, and the first place they leaked hit one of the most fundamental fortresses holding up our modern civilization. This was not an experiment. It was a warning. It was a calculation, and its results threatened to reshape everything in the digital world. Here are the findings. Fast and sharp. The first shock came in 1994. A mathematician. His name was Peter Shor. He didn't build a piece of hardware. He wrote an equation. But this equation was like the theoretical blueprint for an atomic bomb. He knew that the security underpinning the internet, known as RSA encryption, was based on the assumption that factoring large numbers into their prime components is nearly IMPOS-SCI-BLE. By today's standards, this means a 2048-bit key. Take the world's fastest supercomputer. Order it to crack this key. It would take longer than the known 13.8 billion year age of the universe to complete the calculation. This was our digital lock. It was unbreakable, because the math said so. But Shor's algorithm took that math and rewrote it in the language of quantum mechanics. His equation showed this. A sufficiently powerful quantum computer could solve this universe-spanning problem in just a few hours. Hours versus billions of years. This wasn't an acceleration. This was a complete change of the rules. Something that was computationally secure until that day suddenly became mathematically vulnerable. And this was only the beginning. This was a threat on paper. But what if a real machine did it? That moment arrived. In late 2019, Google took the stage with a quantum processor named Sycamore. It wasn't a code-breaking machine. It was something much cleverer. The scientists gave Sycamore the most intentionally worst, most inefficient task for a classical computer to solve, sampling the output of a random quantum circuit. A practically useless task. But that was the point, because Sycamore completed this task in just 200 seconds. Just 200 seconds. The team at Google calculated that the same task would take the world's fastest supercomputer at the time, IBM's Summit, approximately 10,000 years. 10,000 years. IBM disputed the claim. They argued that with optimized classical algorithms, the task wouldn't take 10,000 years, but about 2.5 days. But even this debate proved the main point. 2.5 days. That's 216,000 seconds. 216,000 seconds versus 200 seconds. The difference is still huge. This was the quantum supremacy moment. For the first time, a human-made device, no matter how meaningless the task, had overwhelmingly outperformed its most powerful classical rival. This was no longer a theory. This was a fact etched in silicon. A threshold had been crossed. Effective, and on the other side of that threshold, science fiction was waiting. Because then, in late 2022, physicists using the same Sycamore processor simulated something mind-boggling. A wormhole. Let's be clear, they didn't create a space-time bending tunnel in the lab, but what they did was perhaps more profound. They encoded quantum states onto the processor and manipulated them in a way that reproduced the mathematical dynamics, describing how quantum information would pass through a theoretical wormhole. They used the holographic principle. This principle is a deep idea suggesting that the physics of a higher dimensional space can be fully described by information encoded on its lower dimensional boundary. And what did they find? They showed that the quantum entanglement between two subsystems of the processor produced exactly the signal that would be expected if quantum information had passed through a wormhole connecting these subsystems. It didn't create a wormhole, but it showed that the mathematical description of wormholes and the mathematical description of quantum entanglement are deeply, perhaps fundamentally, interconnected. This was a bridge thrown across that chasm where quantum mechanics and general relativity, the two greatest pillars of science, are incompatible. And it proved that a quantum computer wasn't just a tool for solving practical problems. It was an instrument that could investigate questions about the deepest structure of reality itself. But there was a problem underlying all these shocking achievements. Qubits are fragile. The slightest interaction with the universe, a flicker of heat, a cosmic ray, could ruin the entire computation. This is called decoherence. And it was the Achilles heel of quantum computing. Adding more qubits often just meant adding more noise, more sources of error. Until late 2024, Google emerged with a new processor called Willow, and this processor achieved something that seemed impossible. For the first time, they showed that as more qubits were added to the system, the error rate actually went down instead of up. This was the threshold behavior that quantum error correction theorists had long predicted was necessary for scalable quantum computation. It meant this was the moment you stopped fighting errors and started managing them. It meant the path from millions of noisy physical qubits to just a few thousand flawless logical qubits was no longer theoretical, but demonstrably open. Equations that break codes, experiments that crush classical machines, calculations that simulate spacetime, and finally, an architecture that defeats error. These are not isolated data points, they are pieces of a narrative. But where is this narrative taking us? When we put these pieces together, what is the picture that emerges? Because, as astonishing as these findings are, what's truly frightening is what they imply. These machines aren't just solving problems, they might be shaking the very foundations of our perception of reality. Because these discoveries are not just pushing the limits of computational power, they are striking at the heart of one of the most fundamental scientific quests: drug discovery. Designing a new drug requires understanding how that drug will interact with specific proteins in the human body. Proteins are massive, complex molecules, and their behavior is fundamentally quantum mechanical. Their three-dimensional structure determines their function, and this structure is the result of a process called protein folding. This is one of the hardest problems in biology. But artificial intelligences like DeepMind's AlphaFold have made remarkable progress on this problem by learning from massive databases of known protein structures. But this is not enough, because simulating the full quantum mechanical behavior of new molecules, not just predicting their shape, but modeling how they will interact with drug candidates on a quantum level, remains beyond what classical machines and even AI can currently handle. This is where quantum computers come in. They are uniquely suited to this problem because molecular behavior is quantum mechanical. They don't have to approximate quantum interactions. They can model them directly. What does this mean? It means the much faster development of new drugs, a better understanding of disease mechanisms, and the ability to design molecules with specific properties that classical computational methods can only guess at. This could reduce decades of experimentation to months or even weeks of simulation. This is a revolution that could fundamentally change how we fight everything, from cancer to Alzheimer's. But the power of quantum is not limited to biology. It extends to the largest scales, to the universe itself. Climate modeling requires simulating the quantum mechanical interactions of molecules in the atmosphere and oceans at a level of detail that classical computers cannot achieve. The quantum mechanical processes that determine how greenhouse gases absorb and re-emit infrared radiation, how aerosols affect cloud formation, and how chemical reactions in the atmosphere proceed are all, in principle, accessible to quantum simulation. Classical models approximate these processes with simplified representations, known as parameterizations, which capture average behavior but lose the detail. Quantum simulation could replace these approximations with first-principle calculations. This could potentially increase the accuracy of climate projections on the very scales where current approaches introduce the most uncertainty. Another revolution could happen in energy. Room temperature superconductivity, materials that conduct electricity with zero resistance, has been a holy grail of physics for decades. Such a material could revolutionize energy transmission and storage, eliminating most of the energy lost to resistance in electrical grids. Finding such a material requires understanding the quantum mechanical behavior of electrons in solids at a level of detail that is precisely what quantum simulators are designed to provide. Just these two fields, climate and energy, show how transformative quantum computation could be for the future of civilization. And when we get down to the most fundamental level, to where it all began, particle physics, quantum computers once again take the stage. Facilities like the Large Hadron Collider at CERN produce massive amounts of data from particle collisions, and analyzing this data to detect rare events requires sophisticated computational approaches. Quantum machine learning algorithms are being investigated for particle physics data analysis. Quantum simulations of field theories, the mathematical frameworks that describe particle physics, could illuminate processes that are currently inaccessible to both theoretical calculation and classical simulation. What does this mean? We could test our most fundamental rules about how the universe works. We could study the properties of particles like the Higgs boson with unprecedented precision. We might even find clues about phenomena that still remain a mystery, like dark matter or dark energy. It is like trying to read the universe's user manual, using a machine written in its own language, the language of quantum mechanics. This is not just a new technology. This is a new instrument of discovery for science itself. Broken codes, surpassed computational limits, simulated wormholes, the potential for accelerated drug discovery, and the promise of solving the universe's most fundamental secrets. All these findings and potential applications point to a single truth. We are on the verge of a revolution in what computation means. But how exactly does the engine of this revolution work? What is the source of all this incredible power? What exactly are these machines doing? In temperatures near absolute zero, in circuits too small for the human eye to see, that allows them to solve the universe's most complex problems. We have seen the theory and the results. Now, it's time to enter that dark, cold, and complex void in between, into the heart of those processes. Because, to understand a quantum computer requires understanding not just what it does, but how it does it. And the answer to that how lies in the hardware itself. SO. How exactly do these machines work? Let's stop accelerating and slow down a bit. Because, at this point, we need to descend into those shiny golden chandeliers, into the heart of quantum processors. We've seen the theory and the results. But, now, we must understand the vital link between them, the engineering. How do these devices bring together the most delicate and fragile laws of the universe to solve humanity's most complex problems? The answer lies in a combination of different approaches, and each one tries to tame a different aspect of the quantum world. The first and most well-known approach is superconducting qubits. These are used by companies like Google, IBM, and Rigetti. These qubits are not naturally occurring atoms, they are artificial atoms. Just as a guitar string vibrates at specific notes, these artificial atoms are electrical circuits designed to vibrate at specific quantum energy levels. These circuits are made of two superconducting materials separated by a thin layer that is normally an insulator. This structure is called a Josephson junction, and it is precisely where the weirdness of quantum mechanics emerges. But there is a problem here, because for these quantum effects not to be destroyed by the thermal noise from the room's temperature, these circuits must be cooled to an extreme degree. How cold? Colder than outer space. These processors typically operate at a temperature of 15 millikelvin, which is just 15/100% of a degree above absolute zero. Absolute zero is negative 273.1, 5 degrees Celsius. This is about 200 times colder than the approximately 3 Kelvin temperature of deep space, the coldest known natural place in the universe. This extreme cooling allows the circuits to become superconducting. This means they carry electricity with zero resistance. Therefore, the quantum states can exist for a while without being disturbed by the thermal energy of electrons. The advantage of these systems is that they can be manufactured using existing semiconductor fabrication techniques and operate at high speeds. But the disadvantage is this extreme cooling requirement and the relatively short coherence times. This time, the period a qubit can maintain its quantum state before decoherence destroys it is often only a few hundred microseconds. 2. This means you have to complete the entire computation within this time. That is why some are taking a completely different path. Trapped ions. In this approach, individual ions, atoms that have lost an electron, are suspended in mid-air in a vacuum chamber using electromagnetic fields, like tiny marbles held by invisible tweezers. These ions are then cooled to a point very close to absolute zero using lasers. The quantum states of interest are encoded in the electronic or nuclear spin states of the ions. This means an ion acts like a tiny internal magnet, and this magnet can be either up or down or a superposition of both. The biggest advantage of trapped ion qubits is their incredibly long coherence times. Unlike the microsecond scale lifetimes of superconducting qubits, the quantum state of trapped ions can be preserved for seconds, sometimes even minutes. This is thousands of times longer. Moreover, these systems can perform very high fidelity, meaning very low error, operations. Because each ion is a perfect quantum system created by nature itself, every ion is identical to its counterpart. But this approach also has its challenges, because the operation speeds are slower compared to superconducting qubits, and maintaining individual control over each ion while scaling the system to a large number of ions is difficult. Companies like IonQ and Honeywell are pioneering the commercial development of this technology. They have chosen a slower but more stable path. They aim to perform more reliable computations with fewer but better qubits. This represents a fundamental trade-off between speed and durability. But what if we didn't have to trap qubits in matter at all? What if we could move them at the speed of light? Photonic quantum computing tries to do exactly that. In this approach, quantum information is encoded in photons, particles of light. Photons are natural candidates for quantum information carriers because they interact weakly with their environment. This means they preserve quantum coherence, the superposition, very easily. They are like the hermits of the quantum world. They don't get corrupted easily. Furthermore, they are excellent carriers for quantum communication as they travel at the speed of light through fiber optic cables or empty space. It is precisely this advantage that also creates the biggest challenge, because getting photons to interact with each other is difficult, and this interaction is necessary for the entanglement operations that give quantum computers their power. It's like trying to get two ghosts to shake hands. There are different approaches to solve this. Linear optics approaches use beam splitters and detectors to create entanglement gates probabilistically. Other approaches use matter-based systems to mediate photon-photon interactions. Companies like PsiQuantum and Xanadu are pursuing photonic quantum computing. Their vision is to integrate millions of qubits on a single silicon photonic chip. If this approach succeeds, it could create quantum computers that don't require cooling, operate at room temperature, and can be easily integrated with existing fiber optic infrastructure. This is a vision that has the potential to take quantum computing out of data centers and spread it to a much wider area. Supercooled circuits, laser-trapped atoms, photons at the speed of light. Each one represents a different face of the quantum world, and each one offers different engineering challenges and different advantages. But beyond all these approaches, there is another idea, perhaps the most exotic, the most radical, and the most difficult. An idea that, if successful, could inherently eliminate the biggest enemy of quantum computation, errors. This idea involves encoding information not in a single particle, but in a holistic, topological property of a system. It's like encoding information in the knot of the paper itself, instead of writing on a piece of paper. This approach is so different, it makes the others look conventional. And the name of this approach is topological qubits. And this idea could fundamentally change quantum computation, because topological qubits offer a topologically protected approach where quantum information is encoded in a collective quantum state of many particles. What does this mean? It means the information is stored in a global property of the system, not found in any local feature, just like a Mobius strip has only one side. You can't understand this property by cutting and examining any small piece of the strip. This property belongs to how the entire strip is twisted and glued. It's topology. Topological qubits work with the same logic. Small local perturbations, meaning environmental noise, cannot destroy the quantum information, because the information is not in a single qubit, but spread throughout the entire system. This could significantly reduce the overhead required for error correction, perhaps even eliminate it completely. To realize this approach, scientists aim to use exotic quasiparticles called Majorana fermions. These are strange entities that are both a particle and their own antiparticle. Microsoft has been pursuing this technology for years, Progress has been slow because creating and controlling these Majorana states is incredibly difficult. But in 2023, Microsoft announced it had made progress in demonstrating the basic physical behavior required for topological qubits. A practical topological quantum computer is not yet on the horizon. But if this approach succeeds, it could offer an inherent immunity to the biggest problem all other platforms face: decoherence. This would be a game-changing development. But, in the meantime, another approach is rapidly gaining momentum: neutral atom quantum computers. These systems use individual neutral atoms trapped in arrays of tightly focused laser beams called optical tweezers. Just like placing an egg in each slot of an egg carton, scientists can place individual atoms in these laser traps. These atoms can be arranged in arbitrary two-dimensional or three-dimensional configurations. The quantum states are then manipulated using laser pulses. This approach has shown very rapid progress recently. Demonstrations have been made of systems containing hundreds of qubits, with high connectivity and low error rates. For example, scientists have been able to create programmable layouts with up to 512 qubits using these systems. One advantage of neutral atoms is that, just like trapped ions, they are perfectly created by nature itself. Every atom is identical to every other. But, unlike ions, because they are neutral, they interact more weakly with each other. This isolates them better and provides longer coherence times. However, this is also a challenge because making them interactive for entanglement is necessary. Scientists do this by exciting the atoms to high-energy states called Rydberg states. In this state, the atoms swell up to more than 1,000 times their normal size and begin to interact strongly with each other. Companies like Quera and Pascal are developing this technology. Their goal is to build systems of thousands of qubits and use them for optimization problems and quantum simulations. This is a highly promising approach that combines scalability and flexibility. Above all these different hardware platforms, there is a software layer that makes them usable. Because programming a quantum computer is fundamentally different from programming a classical computer. Classical programs are sequences of commands that change the states of bits. Quantum programs, known as quantum circuits, are sequences of quantum gate operations that manipulate qubits, transform their superpositions, create entanglement, and ultimately produce measurements. It's like composing a piece of music. Each gate changes the note's qubit states to create the final melody, the computation result. To create this composition, quantum programming languages and software frameworks like Qiskit, developed by IBM, are used. Qiskit is an open-source Python library for writing and executing quantum circuits. Google's Cirq serves a similar purpose. Xanadu's Penny Lane is specifically designed for quantum machine learning applications. These tools abstract away the hardware-specific details and allow researchers and developers to write quantum programs that can, in principle, run on multiple hardware platforms. But using these languages is not just about writing commands. It requires understanding quantum mechanics deeply enough to design the specific interference patterns that will amplify the right answers while suppressing the wrong ones. Therefore, quantum algorithm development is a science in its own right. Beyond Shor's factoring and Grover's unstructured search algorithms, researchers are constantly discovering new algorithms. These algorithms offer quantum advantages in areas like linear algebra, optimization, simulation, and machine learning. In the midst of this hardware and software complexity, there is a single central engineering problem that all this effort is focused on: error correction. As we mentioned before, qubits are extremely fragile. Decoherence is the arch nemesis of quantum computation, and this isn't just an engineering problem that can be solved with better materials. It is a fundamental feature of the relationship between quantum systems and the environment. The solution is quantum error correction. Just like error correction codes in classical computers, this approach uses redundancy. It detects and corrects errors by encoding one logical qubit, the qubit carrying the actual information, onto many physical qubits. For example, one of the simplest codes, the surface code, can require hundreds, even thousands of physical qubits to protect a single logical qubit. This ratio depends on the error rate of the physical qubits. The lower the error rate, the less overhead is required. In current systems, this overhead is very large. A computation that theoretically requires 1,000 logical qubits might demand millions of physical qubits when error correction is taken into account. This is why Google's breakthrough with the Willow processor in error correction is so important. The fact that the error rate decreases as more qubits are added to the system was the first concrete proof that this overhead can be overcome, and that scalable, fault-tolerant quantum computation is not a dream. Superconductors, trapped ions, photons, topological qubits and neutral atoms, each represents different paths trying to reach the same goal. They are all trying to control the most fundamental, most bizarre, and most powerful laws of the universe. The hardware is improving, the software is maturing, and real progress is being made against the biggest obstacle, the problem of errors. We understand the technical details, we've seen the different approaches, but what's truly exciting is what will happen when all these pieces come together. What will happen when these machines start working with millions of flawless qubits, attacking real-world problems? What will happen when Shor's algorithm shatters digital locks? What will happen when quantum simulators design new drugs or materials atom by atom? We are approaching the climax, where theory and engineering end, and application and consequences begin. And at that point, the world may never be the same again. Because now it is time for the tempo to increase again. Because now we are coming to the moment when everything changes. And now we come to the true climax. Because now everything changes. Put aside theory and engineering. Now, we will see the moments when this new power attacks some of humanity's oldest and deepest questions. This is not just the rise of a technology. This is an earthquake in which science itself is being rewritten. This is a paradigm shift. The tempos are increasing. The sentences are shortening. Because now we will witness the moments when quantum computers are not just computing, but unraveling the very fabric of reality. This is a revolution. And like every revolution, it takes victims. The first victims will be our old, safe, comfortable theories. Be ready, because what comes next may make you question everything you know. The first great shock, the year 1900. A physicist named Max Planck was trying to explain a phenomenon called black body radiation. This is the spectrum of light emitted by hot objects. Existing theories predicted that hot objects should emit an infinite amount of energy at short wavelengths. This was so obviously wrong that it was called the ultraviolet catastrophe. To prevent this catastrophe, Planck did something radical. He assumed that energy is not continuous, but instead comes in discrete packets he called quanta. Even he didn't believe this was physically real. He just thought it was a mathematical trick that produced the right numbers. But he was wrong. These packets were real, and this single idea was the first bomb thrown at the glorious, seemingly complete edifice of 19th century classical physics. Newton's mechanics, Maxwell's equations, thermodynamics, they all worked perfectly. Physics seemed finished. But that single paper by Planck opened a crack in the foundation of this building. Because if energy is discrete, then could reality itself be discrete? This idea was contrary to every intuition at the time, but without it, the spectrum of blackbody radiation could not be explained. This was proof for the first time that nature does not have to conform to our intuitions. It was the first sign that mathematics could reveal a deeper truth than our senses. The scientific world would spend decades trying to understand what this idea fully meant. But in that moment, a new era had begun. The classical world was dead. The quantum age was born. And it was all because of a single number, Planck's constant 6.626 x 10 negative 34 joule seconds, one of the most fundamental constants of the universe, and the beginning of the end of ignorance. But the real bomb exploded in 1905, Einstein, and the photoelectric effect. The effect was simple. When you shine light on certain metals, electrons are ejected. But there was a weirdness here. No matter how intense the light was, if its frequency was below a certain threshold, not a single electron was ejected. But if it was above the threshold, even the faintest light ejected electrons immediately. According to classical wave theory, this was im pos psi bell, because a wave's energy depends on its intensity. But Einstein took Planck's idea of quanta one step further. He proposed that light itself is composed of discrete particles, which would later be called photons. Each photon carried an energy proportional to its frequency. This perfectly explained the photoelectric effect, and it won Einstein the Nobel Prize in Physics in 1921. But it achieved something much bigger. It proved that light is both a wave and a particle at the same time. This was a fact that shattered every classical intuition. How can something be both a localized particle and a spread-out wave at the same time? It was counterintuitive, but the experiments didn't lie. Light behaved either like a wave or a particle, depending on what you measured. This was the first seed of the idea that the observer affects the observed. It was the moment when the question of what reality does when we are not looking at it was first asked seriously. This discovery didn't just explain a phenomenon, it demolished our most fundamental assumptions about the nature of reality, and it asked science this question: if light is this weird, what if everything is weird? And the weirdness continued. 1913. Niels Bohr, and the structure of the atom. Classical physics predicted that electrons orbiting atomic nuclei should continuously radiate energy and spiral into the nucleus in a fraction of a second. This meant all atoms should collapse instantly. But when we look around, we see that atoms are quite stable. This was a paradox. To solve this paradox, Bohr once again resorted to the quantum idea. He proposed that electrons can only exist in specific, discrete orbits, and each orbit corresponds to a specific energy level. Electrons could only radiate or absorb energy by jumping between orbits. No other orbits were allowed. This was an arbitrary and unexplained claim within any existing framework at the time. But this model produced predictions that matched experimental observations with incredible precision, especially the spectral lines of light emitted by the hydrogen atom. Each spectral line corresponded to a quantum leap of an electron from one specific orbit to another. This showed that the atomic world was not continuous like the orbits of planets, but discrete like the rungs of a ladder. The electron was either on one rung or another. There was no in-between. This was the first evidence that matter itself is fundamentally digital. We thought we lived in an analog universe, but Bohr showed that at the smallest scales, the universe is actually made of pixels, of discrete quantum states. This was the final nail in the coffin of classical physics. But all these individual discoveries were just symptoms of a deeper, more unified theory. And that theory came in the 1920s with the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Max Born. This was the golden age of quantum mechanics. Heisenberg formulated quantum mechanics in terms of matrices, abstract mathematical arrays that encode the observable quantities of a system and their relationships. Schrödinger reformulated the same physics as a wave equation, which describes how the quantum state of a system evolves over time. This equation is one of the most important equations in modern physics. Dirac synthesized these two approaches and expanded quantum mechanics to make it compatible with special relativity, which led him to predict the existence of antimatter. And Max Born provided the probabilistic interpretation. Schrödinger's wave function did not describe a physical wave in space. It encoded probability amplitudes, mathematical quantities whose squared magnitudes give the probability of observing specific outcomes when a measurement is made. This was the idea that Einstein resisted for decades. The idea that physics is not deterministic at the fundamental level. The idea that there is no truth about an electron's position before it is measured, only probabilities, was deeply unsatisfying to him. He insisted that God does not play dice, but the experiments, time and time again, showed that not only does God play dice, but those dice are entangled, and their outcomes are correlated in ways that our classical intuitions cannot grasp. This was the pinnacle of science. It was the most successful, most precise, and most bizarre theory ever produced by the human mind. All these technical breakthroughs, these incredible theoretical leaps, these seemingly impossible discoveries, they are not just academic curiosities. They are the fundamental building blocks that make quantum computers possible today. But when these building blocks come together, what emerges is not just a fast computer. What emerges is a machine that asks philosophical questions about reality itself. Because if the universe is fundamentally quantum mechanical, and it seems that it is, then could the universe itself be performing a computation? Every particle interaction, every collision, every decay, every absorbed or emitted photon is a quantum mechanical event that processes information according to fixed rules. The evolution of the universe from the Big Bang to the present day can be understood as a single, unimaginably large computation playing out across space and time. This is not mysticism. This is a natural consequence of taking quantum mechanics seriously as a description of physical reality. And if the universe is processing information, and we are part of that universe, then what do the quantum computers we build mean? Are they small, carefully controlled pieces of the universe that we use to perform computations that mimic the universe's own processes? The answers to these questions take us not just to the limits of technology, but to the limits of existence itself. And at this limit, everything gets even weirder, because now we will take all this information and turn to the deepest, darkest, and most unsettling question. Are these machines just simulating reality, or are they recreating reality? Therefore, these machines are not just passive observers, they are active participants, engaging with the fabric of reality at the most fundamental level. And this participation has led to the most incredible, most unsettling discoveries. Now, we go to the very edge of science. We are speeding up, because these moments do not deserve to be told slowly. They are like lightning, striking the mind and illuminating everything. The first bolt of lightning, Heisenberg's uncertainty principle. This is often misunderstood as a limitation of measurement, as if the problem is that measuring one thing disturbs another. But the reality is much deeper, much stranger. This principle is a fundamental statement about the structure of reality itself. Certain pairs of physical quantities, position and momentum, energy and time, are fundamentally complementary in quantum mechanics. They cannot both have precise values at the same time. This is not due to our lack of precision. It is because the certainty of one is mathematically incompatible with the certainty of the other. The uncertainty is not imposed by the act of measurement. It is inherent to the quantum state itself. What does this mean? It means you can never know both exactly where an electron is and exactly where it is going. Never. The universe does not allow it, because the more precisely you know one, the more uncertain the other becomes. This is a rule of nature, and this rule has direct consequences for quantum computing. Quantum information cannot be copied. This is a result known as the no-cloning theorem. If someone tries to secretly listen to a quantum communication and copy the quantum states, the very act of copying will introduce detectable errors. The security of quantum key distribution is based on this very foundation. This is the first time in history that security is based not on mathematical difficulty, but on physical impossibility. This means that nature itself is a confidant. But there was something even more unsettling: entanglement, that strange connection that Einstein called spooky action at a distance. When two particles become entangled, their quantum states can no longer be described independently. Instead, their combined state is described by a single quantum state that encompasses both particles simultaneously. Measuring one particle and finding it in a specific state does not cause the other particle to enter that state. Rather, the measurement reveals information about the shared state that always existed, a correlation that existed in the entangled state before any measurement was made. How real was this? John Bell, an Irish physicist in the 1960s, gave a mathematical answer to this question. He proved that if these correlations were caused by hidden local variables, a classical mechanism we hadn't yet discovered, they would have to satisfy certain inequalities. But then, tests conducted by Alan Aspect and his colleagues, starting in 1982 and becoming increasingly precise over the following decades, consistently violated these Bell inequalities. The correlations in quantum mechanics were stronger than any local realistic theory could produce. What did this mean? It meant that entanglement was not some form of classical correlation we just didn't understand yet. It was a genuinely non-classical phenomenon, with no classical analogue. Alan Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics in 2022 for their experimental work on entanglement and the violations of Bell inequalities. The Nobel Committee's citation explicitly noted the importance of their work in enabling quantum information technologies, including quantum computing and quantum cryptography. This was the moment when a philosophical curiosity became the foundation of a technological revolution, and this revolution created its own language: quantum information theory. Claude Shannon developed classical information theory in 1948, laying the mathematical foundations for how to measure, transmit, and compress information. His central insight was that information is physical, but quantum information theory extends Shannon's framework to quantum mechanical systems. And in this new language, the word impossible gains a new meaning: quantum teleportation. The name is misleading. It does not transport matter instantly across space. But what it does is perhaps more profound. It transfers a quantum state, the complete quantum mechanical description of a particle, from one location to another, using a shared entangled pair and a classical communication channel. The sender has a particle in an unknown quantum state. They have previously shared an entangled pair with the receiver. The sender performs a measurement involving their particle and the one they want to teleport, then transmits the classical result of this measurement to the receiver through an ordinary communication channel. The receiver uses this classical information to perform a specific operation on their particle from the entangled pair. After this operation, the receiver's particle is in the exact same quantum state that the sender's particle was in before the measurement. Vitally, the quantum state of the original particle is destroyed in the process. This conforms to the no-cloning theorem. The state is not copied, it is moved. And this transfer cannot happen faster than the classical communication carrying the measurement result, SO. It does not violate the speed of light, but it shows that quantum states can be transferred between particles without sending the particles directly. This is the foundation of the quantum internet, a network that connects multiple quantum computers or communication nodes through quantum channels. China's Maisha satellite achieved a milestone in this field in 2017 by demonstrating satellite-based quantum key distribution over distances of more than 1,000 kilometers. This was proof that a global-scale quantum network was no longer a science fiction dream. Uncertainty, entanglement, teleportation. These are the most mind-bending, most unsettling truths of the quantum world, and these truths are not just theoretical games. They form the basis of the most powerful tools ever built by humanity. But in the midst of all these incredible scientific breakthroughs, it is time to pause, breathe, and think. Time to get off the roller coaster for a moment and question what the view means. We have asked the question, what can these machines do? We have asked the question, how do these machines work? But now, we must ask the hardest, most personal and most important question. What does all this mean for us? Who are we? As beings living in a universe that is fundamentally probabilistic, uncertain, and entangled, how should we understand our own existence in the light of this new science? Because the real revolution is not in the chips or the equations. It must take place in our minds. And that revolution, is it just simulating, or is it recreating? But now is the time to stop and think. Time to get off the roller coaster, take a breath for a moment, and look around. Because all this technology, all this science, all these dizzying discoveries ultimately serve a single question: what is our place in this picture? Who are we, as beings living in a universe that is fundamentally probabilistic, uncertain, and entangled? Quantum computing is changing not just our computers, but also our understanding of ourselves. Because, in the light of this new science, we are forced to confront the deepest paradoxes of our own existence. This is not a story of technology. This is a story of humanity. And this story is a story of opposites. Because, on one hand, there is the mind-boggling complexity of the universe that quantum computing shows us. The fact that the possible sequences of a coin tossed 266 times exceeds the number of atoms in the observable universe. This means the universe is not fundamentally simple, but rather has a complexity far beyond our cognitive capacity. Our brain evolved to find patterns, to simplify, to create shortcuts for survival. But the universe needs no shortcuts. It processes every single possibility, every interaction, every quantum state in excruciating detail. On the other hand, there are us existing within that universe. Our brain, that modest organ accustomed to linear thinking, unable to grasp this exponential complexity. How can this be? How is it that the universe harbors such bottomless complexity, while we, as its most intelligent beings, can only scratch its surface? This holds a kind of tragic truth. We will never fully grasp the full complexity of the universe, all its interdependent structures, all its quantum interactions. It is a fact that no machine, no matter how powerful, can ever capture the entirety of the universe. We are like children, standing on the shore of this cosmic ocean, playing with only a few pebbles. The depth of the ocean will always remain a mystery to us. This can create a kind of cosmic loneliness and sense of inadequacy. But, and here comes that beautiful but we know that ocean exists. We are trying to measure the depth of that ocean. Quantum computers are the most advanced probes we have sent into this ocean. They allow us to take a slice of the universe's complexity, a manageable piece, and understand it. Yes, we will never model the entire universe, but that doesn't mean we can't model anything. Quantum computers, by allowing us to model useful slices, molecules, materials, even space-time itself, turn this tragedy into a triumph. You are also in this paradox. While your mind lives in a world reduced to the simple patterns of daily life, you are also part of a universe where numbers like 2 to the power of 266 exist. You are part of this tragic beauty. You simultaneously experience the sorrow of knowing the limits of your understanding and the excitement of pushing those limits anyway. And there is another contradiction, the relationship between computation and reality. MIT physicist Seth Lloyd proposed that the universe itself can be understood as a quantum computer. This is not a metaphor. This is a precise description of what the universe is doing every moment. Every particle interaction is a part of the universe's grand computation. In this framework, a quantum computer is not something separate from the universe, making calculations about it. It is a small, carefully controlled part of the universe, performing computations that mirror the universe's own processes. When a quantum computer simulates a molecule, it uses quantum mechanical processes to model quantum mechanical processes. The simulation and reality speak the same mathematical language. This is an incredibly powerful idea. But, on the other hand, there is the fact that our scientific models are always representations, maps, never the territory itself. The Schrödinger equation is the mathematical backbone of quantum mechanics. But this equation is a human-built, compressed, elegant representation of something the universe simply does without referring to any equations. How can this be? On one hand, we have the power to build machines that speak the same language as the universe. On the other hand, there is the fact that this language will always be a translation, a simplification. This is a tragic limitation. We will never be able to touch reality itself fully. We will always be looking through the veil of our models, our theories, and our equations. This is a modern version of Plato's cave allegory. We look at the shadows on the wall, our models, and believe they are real. But the real world, the universe itself, will always remain just beyond our grasp. But, and there's that but again, but we can create those shadows, and those shadows are becoming increasingly accurate, more precise, and more useful. Google simulating wormhole dynamics on the Sycamore processor was not a stunt. It was an indication that the boundary of knowable things is moving. Those shadows are giving us increasingly clear clues about what is outside the cave. You are also in this cave. Your daily life, your work, your relationships, they are all models, simplified versions of reality. But, at the same time, you have the ability to question these models, to make them better, and even to create new models, new machines, that speak the same language as the universe itself. You are both condemned to the shadows and the creator of those shadows. And there is one last contradiction, perhaps the most personal one: time. Quantum computation offers us the ability to confront both unimaginably long and incredibly short timescales. On one hand, there is the time it would take a classical supercomputer to break a current 2048-bit RSA key, longer than the 13.8 billion year age of the universe. This is a time the human mind cannot comprehend. It is a time frame almost equivalent to eternity. It confronts us with our transience, how meaningless a single human life is on this cosmic calendar. On the other hand, there is the time it would take a quantum computer to solve the same problem. Hours. Suddenly, that cosmic, unreachable timescale becomes a manageable part of human life. How can this be? What does it mean for a problem's difficulty to drop from the age of the universe to a few hours? This shows that time itself, at least in terms of computation, is not an absolute thing, but a flexible concept that changes depending on the tools we use. This tragically reminds us, our biologically limited lifespan of about 80 years is less than a blink of an eye in the grand scheme of the universe. There are problems we will never see solved. There are theories we will never live to understand. This holds an inevitable sadness. We live under the tyranny of time, but quantum computation promises a rebellion against this tyranny. With its potential to reduce processes that normally take decades, like drug discovery, to months, it carries the potential to gift us time. It gives us the chance to see, within our own limited lifetimes, solutions that normally not even our grandchildren's grandchildren would see. This is like bending time itself, accelerating it, compressing it, and putting it at the service of humanity. You are also in this flow of time. You are aware of your own mortality. You feel how fast time flies every day. But, at the same time, you are part of the collective of humanity. And humanity, right now, is creating tools that will redefine its relationship with time itself. Your individual time may be limited, but the time of humanity with these new tools may be much longer than we thought. Complexity and simplicity, reality and representation, cosmic time and human time. These contradictions are proof that quantum computation shows us not just what we know, but also who we are. But this philosophical journey doesn't end here, because beyond these contradictions lies a deeper, more fundamental question. If these machines speak the language of reality, then what can we learn about that language itself? This is a journey that takes us to the nature of knowledge, the origin of space and time, and perhaps the ultimate question of everything. And on this journey, we encounter a new set of contradictions, because these machines show us how bizarre not just the universe is, but the nature of information itself. On one hand, there is classical information, reliable, copyable, and deterministic. A bit is either a 0 or a 1. Information can be transferred from one place to another without loss. Our digital world is built on this foundation. On the other hand, there is quantum information. It is fragile. It cannot be copied, and it changes the moment it is measured. The no-cloning theorem states that it is impossible to make a perfect copy of quantum information. At first glance, this seems like a flaw. How do you back up the state of a qubit like you back up classical data? The answer: you can't. This is a tragic fragility inherent in the nature of quantum information. It can decohere at any moment, be swallowed by environmental noise, and be lost forever. For us, living in the information age, this seems like an unacceptable limitation. We expect everything to be permanent, storable, and reproducible. But this fragility is also its greatest strength, because the inability to copy information makes it impossible to eavesdrop on. Quantum key distribution builds its security on this very impossibility. When an eavesdropper tries to measure the information to steal it, they inevitably disturb it and reveal their presence. This means that the information itself ensures its own security. This fragility is not a weakness, it's a feature. You too navigate between these two types of information every day. On one hand, you have your emails, your photos, your copyable and storable digital identity. On the other hand, you have the uniqueness of a moment, the singularity of a conversation, the lived experiences that can never be fully recreated. Quantum information is perhaps more like the latter, fragile, transient, but for that very reason, valuable and secure. And this brings us to another paradox: loneliness and connection. When we look at the universe, we see an unimaginable emptiness and loneliness. Proxima Centauri, the star closest to us, is 4.24 light-years away. This means that even light, traveling at 300,000 kilometers per second, takes more than 4 years to reach it. Galaxies, are like lonely islands floating in the cosmic ocean, millions of light years apart from each other. The 15 millikelvin temperature we use to cool quantum computers creates an environment even colder, more isolated than the universe itself. This shows that at the most fundamental level, quantum computation requires extreme isolation. The qubits must be shielded from the rest of the world, even from the universe itself, to perform a meaningful computation. This is a tragic fact, that the deepest connection requires the deepest loneliness. But at the heart of quantum mechanics lies a principle that shatters this loneliness: entanglement. When two qubits become entangled, they become instantly connected, no matter the distance between them. A measurement on one instantly determines the state of the other. This is a spooky action at a distance that implies the universe is not local at its most fundamental level, that everything might be connected in some way. This shows that the universe is a network, a structure connected by invisible threads. This connection gives us hope, because it means that no matter how lonely we may seem, we are all actually part of the same quantum fabric. You too experience this dilemma. Sometimes you may feel lonely, disconnected from the world, trapped in your own thoughts. This is your personal, cosmic isolation. But, at the same time, you are connected to your family, your friends, even people you've never met, by invisible bonds. A smile, a word, an action can affect someone miles away. Just like an entangled particle, your existence is not separate from the rest of the universe. You're both a lonely island and part of the ocean that connects those islands. And finally, the relationship between information itself and the mystery of consciousness. On one hand, as quantum computers show us, the universe processes information at its most fundamental level. As physicist John Archibald Wheeler summarized with his phrase, "it from bit," and later, "it from qubit," the universe itself might be a giant quantum information processor. Every physical quantity can ultimately be reduced to information, to quantum states. This suggests the idea that reality is fundamentally mathematical and computable, that with a powerful enough computer, we could solve all the secrets of the universe. On the other hand, there is a subjective experience that emerges within that universe and observes it: consciousness. What consciousness is, how it arises, is one of the greatest mysteries of science. How do subjective experiences like the redness of red, the sadness of a melody, or the warmth of a memory arise from the firing of neurons, from purely physical and chemical processes? This is known as the hard problem, and quantum computation is far from offering an answer to this problem. This shows a tragic limit of our technology and our understanding. We may be on the path to building machines that can simulate the universe itself, but we cannot explain what it means to experience that universe. But perhaps these two are not so separate after all. Some theorists suggest that consciousness itself involves quantum phenomena, especially coherence and entanglement. This is a highly speculative field, and far from being proven, but if it's true, it implies that consciousness is not something separate from the universe's information processing, but rather its most complex, most refined, and most introspective expression. This suggests that the universe is not just computing, but is also becoming aware of itself, and that awareness is us. You are at the very center of this mystery. You are a biological machine that processes information. The billions of neurons in your brain perform trillions of computations every second. But you are more than the sum of these computations. You are an experience. You are the part of the universe that questions itself, feels itself, and tries to give meaning to itself. You are both the computation and the unique, ineffable sensation that arises from that computation: fragility and strength, loneliness and connection, computation and consciousness. These contradictions paint the philosophical landscape that the quantum world offers us. We now know that reality is stranger, more complex, and more deeply connected than we thought. We now know that we have not only limits to our understanding, but also the power to push those limits. But beyond all these thoughts, a more personal, more fundamental question may lie. In the face of this new picture of reality, what do we feel? Does this knowledge excite us or frighten us? Does it make us think about how special our place in the universe is, or how insignificant we are? Perhaps the answer, like a qubit, is a superposition of both. Perhaps true wisdom is the ability to embrace both of these contradictory feelings at the same time, because this philosophical journey forces us to understand not just the universe, but ourselves better. And in the depths of this understanding, there are many more layers waiting to be discovered, because this story is not over yet. It is just beginning, and in the depths of this understanding, there are many more layers waiting to be discovered, because these philosophical confrontations lead us to another place, a more internal inquiry. The question is no longer what the universe is, or what our place in that universe is. The question now is, what do we do with this knowledge? How should these strange, counterintuitive but proven truths of quantum mechanics shape our daily lives, our decisions, and most importantly, our relationships with each other? This is where science ends and wisdom begins. This is the moment when the equations fall silent and the human heart begins to speak. And on this inner journey, we also face our own contradictions. On one hand, there is the idea of universal connection that quantum mechanics offers us. Entanglement whispers the possibility that everything is somehow interconnected, that separation may be an illusion. This places a deep responsibility on us, the idea that our actions, our thoughts, our words can create ripples that spread through the universe in ways we can never see, never know. On the other hand, there is the individualism and separation that modern society pushes us towards. Our own goals, our own achievements, our own identities, our social media feeds, our echo chambers, algorithms that bring us together with those who are like us and separate us from those who are not. How can this be? How is it that while the most fundamental law of the universe seems to be based on connection, the society we have built is so focused on separation? This is a tragic disconnect. We live isolated lives in an entangled universe. While the universe tells us unity, we insist on me. This is not just a philosophical contradiction. It is a tension that lies at the root of many of today's biggest problems, from the climate crisis to social injustice, because these problems stem from our ignorance of the fact that our actions are interconnected. But this knowledge is also a call to action. If entanglement is real, if connection is a fundamental principle, then we can apply this principle not just in quantum computers, but in our own lives. This offers a scientific basis for more empathy, more compassion, and more cooperation. It is to understand that at the most fundamental level, there is no such thing as the other. You are also in this tension. Every day, you try to strike a balance between your individual goals and your responsibilities to your family, your community, and the planet. Quantum mechanics can remind you which side is more fundamental in this balance. It can whisper to you how empty individual success is without collective well-being. You are both an individual and a part of that invisible network that connects those individuals. The choice is yours. And there is another contradiction: the power of knowledge and the weight of knowledge. Quantum computing promises us immense power. The power to cure diseases, to fight climate change, to solve the secrets of the universe. This is an unprecedented capability in human history. A tool like Shor's algorithm has the power to reshape the global financial system and national security. This knowledge is exciting. It gives us hope that the future can be under our control, that our biggest problems can be solved. On the other hand, there is the crushing responsibility and moral burden that this knowledge brings. Who will control quantum computers? Who will wield this power? What if this technology further deepens existing inequalities? What if this power makes the rich richer and the powerful more powerful? Will the bright future that quantum promises be valid only for a select few? These questions carry a tragic weight, because we know from history that technological progress does not guarantee moral progress. The knowledge of splitting the atom gave us both clean energy and nuclear weapons. The same knife can both save a life and take a life. Quantum computing is no different. It could be the sharpest knife humanity has ever held. And how we will use this knife is the biggest unanswered question. But the very fact that we are asking these questions is a sign of hope. It means we see technology not just as a tool, but also as a moral choice. It means we ask not only, can we do it, but also, should we do it? This moral inquiry is as important as the technology itself, because, in the end, what will determine the future of quantum computers is not the coherence time of qubits, but the strength of humanity's conscience. You are also a part of this moral equation. As you watch the development of this technology, you consider not only its potential benefits, but also its potential risks. You can raise your voice for this technology to be used in a fair and equitable way. You are not just a spectator, you are a moral actor who can shape the future direction of this technology. Power and responsibility are on your shoulders too. And one last contradiction, our search for certainty and the probabilistic nature of the universe. The human mind loves certainty. It wants clear answers, specific rules, a predictable future. A large part of our scientific history is the search for this certainty. Newton's laws gave us a deterministic universe that worked like the mechanism of a clock. Everything had a cause and an effect. With enough information, we could predict the future perfectly. On the other hand, there is the probabilistic reality at the heart of quantum mechanics. At the most fundamental level, the universe plays dice. You cannot know for sure where an electron will be in the next moment. You can only calculate the probabilities. This is one of the things the human mind has the most difficulty accepting. It is the idea that we are not in control, that the universe is fundamentally uncertain. This is a tragic loss, the death of our dream of certainty. We can no longer take refuge in the comforting thought that we can know and control everything. The universe does not play by our rules, but this probabilistic nature is also the source of creativity and freedom. If everything were predetermined, then how would it be possible for something new to emerge? A work of art, a new idea, a love. These are all unpredetermined events that emerge from a sea of possibilities. Quantum uncertainty shows that the universe is not a frozen statue, but a living process, constantly recreating itself. Superposition is not just the coexistence of different states, it is potential itself. It is proof that the future is not yet written. You too live your life in this uncertainty. You cannot know for sure what will happen tomorrow. There are so many things you cannot control. And this can sometimes be frightening, but at the same time, this uncertainty is your freedom to choose. It is your ability to shape your future. Every day, you choose a specific reality from your own superposition state. Every choice you make turns a possibility into reality. You are not a cog in a deterministic machine. You are a quantum being, navigating a universe of probabilities, creating your own future. Connection and separation, power and responsibility, certainty and uncertainty. These deeper layers show that quantum science can teach us not only about the universe, but also about what a good life means. But even this inner journey has not yet reached its final destination, because there is a point where all these thoughts, all these contradictions, intersect. The place where the question of what reality itself is reaches an ultimate answer, and that place is the ultimate answer to the question of what reality itself is. And this answer is perhaps much more surprising than we expected, because this final philosophical layer takes us to the origin of space and time, to that deepest structure at the foundation of everything. This is the most radical implication of the holographic principle and the ADS-CFT correspondence. On one hand, there is the three-dimensional, seemingly concrete space-time we live in, move through, and experience. This is the stage of our reality. On the other hand, there is the idea that this three-dimensional stage is actually an emergent phenomenon from quantum information relationships on a lower dimensional boundary. Just as a two-dimensional hologram creates a three-dimensional image, how can this be? How can this solid reality we live in, touch and feel, be a reflection, a projection of something more fundamental? This is an idea that pushes the limits of the mind. It tragically means that reality itself might be a kind of illusion. The ground we thought was solid might just be the tremors of a more fundamental quantum information network. This shakes the most basic assumption of our existence, the assumption that the space we live in is fundamental and real. But this idea is also incredibly beautiful and unifying. If space-time emerges from quantum entanglement, then the most fundamental thing in the universe is not matter or energy, but information, connection. This means that gravity, the curvature of spacetime, is actually the geometric expression of the entanglement network between billions and billions of qubits. This is a bridge that could unite the two greatest pillars of science, general relativity and quantum mechanics, by connecting one of the universe's greatest mysteries, gravity, to the mystery of the smallest scale, quantum entanglement. You're also part of this holographic universe. Your existence is not just the sum of your atoms. You are an expression of that complex entanglement network that connects those atoms to each other and to the rest of the universe. Your three-dimensional body is perhaps a reflection of a two-dimensional set of information encoded on the boundary of the universe. This does not make you less real. It makes you more deeply connected to the most fundamental fabric of the universe, information, than you could ever imagine. And this brings us to the final contradiction in this journey, the limit of knowledge and the infinity of curiosity. On one hand, there is the dizzying accumulation of knowledge brought by scientific progress. Quantum mechanics gives us an incredibly precise and accurate picture of how the universe works. Quantum computers, using this knowledge, have the potential to solve problems that were previously unsolvable. Our knowledge is increasing every day. The boundary of knowable things is constantly expanding. On the other hand, there is the fact that every new discovery, every new answer, gives rise to more questions. We understood black body radiation, but that led us down the rabbit hole of quantum weirdness. We proved that entanglement is real, but that pushed us to question the nature of spacetime. We are building quantum computers, but this makes us ask deeper questions about the nature of information and consciousness. This is the tragic, but also magnificent, nature of science. The horizon constantly recedes as we walk towards it. Every answer opens the door to a bigger, harder question. We may never reach an ultimate answer, that final equation that explains everything. The peak of the mountain of knowledge may always remain hidden behind the next hill. But isn't the journey itself more important than the destination? Isn't this endless curiosity, these unanswered questions, what makes us human? If we knew all the answers, what would we live for? Wouldn't the death of curiosity also be the death of the human spirit? This is perhaps the deepest lesson that quantum mechanics teaches us. The universe is not just a problem to be solved, but an infinite mystery to be admired, to be wondered at. And quantum computers are the most powerful tools we have built not to solve this mystery, but to appreciate it more deeply. You are also a carrier of this infinite curiosity. From the first moment you looked at the sky as a child and wondered about the stars, to the moment you are reading these words today and thinking about the nature of the universe, it is this curiosity that has carried you forward. It is the desire to keep asking the right questions. Even if you can't find the answers, you are the part of the universe that wonders about itself. And this curiosity is your greatest strength. As we approach the end of this journey, how do we feel? On one hand, that feeling of smallness and insignificance we feel in the face of the unimaginable size and complexity of the universe. On the other hand, that incredible sense of pride and wonder brought by the mind that can understand that universe, speak its language, and even use its processes for our own purposes. Fear and excitement, inadequacy and power, sadness and hope. Perhaps they are all correct. Perhaps the quantum truth requires us to embrace these contradictory feelings at the same time, because we are both stardust and the consciousness that becomes aware of that stardust. We are both a momentary product of the universe and the beings that tell the story of that universe's billions of years. Accepting this paradox is perhaps the first step to living wisely in the quantum age. Thus, we have made a journey from the abyss of complexity to the nature of reality, from the emptiness of loneliness to the power of connection, and from the weight of knowledge to the infinity of curiosity. We now know that quantum computers are not just faster machines, they are philosophical tools that fundamentally change our relationship with reality. They show us that the universe is not a deterministic mechanism ticking like a clock, but a network full of possibilities, constantly recreating itself, living, and deeply connected. And they remind us of our place in that network, our responsibilities, and our potential. This journey has answered many questions, but it has raised even more. And perhaps most importantly, it has taught us a single, ultimate truth. The universe begins to tell its story when we begin to listen. And this story may be the most beautiful, most bizarre, and most hopeful story we have ever heard. Now, it is time to bring all that we have learned together, and, as we stand on the threshold of this quantum revolution, to say the final words on how we should look to the future. In this journey, we saw how quantum mechanics bends reality. But there's something I didn't tell you. This bending may not stay in the subatomic world. Physicists are working on theories that we could bend spacetime itself, warp drives, wormholes. On our next journey, we will go beyond the speed of light. Are you ready?